Record. Okay, so.
Matt, did you try to bike to work today, or did you stay home?
Well, if you look in the background here, it probably looks a little different than it usually does. See the Alps in a picture in the background. I'm in my basement. So no, I didn't even try. I have a road bike for one thing, and you know, I'm a guy who likes to, you know, to be challenged, but I think my senses came to me today, and I'm like, well, look, I've got a computer here. Let's try it this way instead of trying to be a manly man. I'm gonna do things from the basement. So, but yeah, it's, you know, it wouldn't put it past me sometimes to try that. I felt over the weekend some slight symptoms, and that's another concern I have. I don't know. I have something, I don't know what it is, and obviously there's the concern then about, you know, being safe and so forth. So, that's the real reason. Otherwise, I would have tried it, to be honest, Matt. So, so I'm in the basement. I'm trying Zoom down here for the first time, and hopefully things will work out fine. But just giving you a heads up, if there's any issues, that might be it. If you see anything weird, you know, just don't hesitate to let me know. I did hit the record button, so we are recording this morning. And where are we at? We have you guys basically have finished homework 5, right? And I posted the project timeline, and you know, so what do we have here? About maybe 7 weeks or so left in the course. And so this week, I think I said by Friday, I would like you guys to turn in, you know, just a basic summary and some basic research questions associated with your data. So you don't have to do a hardcore analysis or anything, but obviously you need to pick your data and be comfortable with the data that you have. Look at it, try to understand it, think of questions that may be of interest with it. And then I posted a few other things, you know, just some basic questions to answer. So that's the first step. And then, you know, you start looking at it, you know, making some graphs, explore your data a little bit. Like I said in the timeline, I typically met with students, each student, you know, for 15 minutes. And I'm not making that requirement this year, but I still think it would be a good idea for you to reach out to me. And what we can do, if you want to, you know, we can either just email, or we can talk on phone, or we can actually use the link to this class, because it's set up as a continuous link. So I'm going to leave the ball in your court, though. So if you want to talk to me about your data and about the methods that you're trying, and then I can give some input about, you know, maybe some suggestions for you about what you can do. I would just suggest don't wait till, you know, a couple days before, you know, the presentation or whatever. Try, if you can, to reach out to me early. Like I've found in the past, I've taught this course many years, and there's never, hardly ever a case where somebody shows me something, it's like, oh, you're perfect, there's no questions or anything. So I think there's some benefit that you'll have by talking to me, but I'm not making it a formal requirement this year. Any questions that anyone has on the project? Okay, just let me know if there is, if anything comes up. So otherwise, you're done with homework 5, and I think more likely we'll probably have 2 more homeworks left in this course. So you're, on your way to being finished. I want to space out the homeworks now, so that you have some time to devote to your project. And there may be one at the end where I assign some questions, but I don't collect it. So expect probably a couple more homeworks in this course. And then towards the end of the course, we'll have like a couple days devoted to your presentations. So those will be fairly short, and I want to keep it kind of informal. I don't want to make it like a high pressure thing where you're worried about, your delivery and everything. Just come in and just treat it as you're sharing what you did. And so it's going to be more of a discussion. Obviously it's good practice. It's good practice to do this because, we all need to learn how to communicate when we have jobs, and you want to be able to present, analyses that you've done to people. So I think it's good practice. And I also want people in the audience to ask questions. So I want it to be kind of a discussion type of format. So these are things just to, keep in mind. That's a ways off still, but just keep that in mind. Anything else? If not, we are going to march forward. So today we're going to start talking about generalized linear mixed models. Okay, so we start building up, from 6612 or even 6611. You learn about general linear models. So the basic tool that we have for, simple linear regression, multivariate regression, or I really should say multivariable regression. It's not really a multivariate technique. And that's something that non-statisticians probably wouldn't appreciate, but multivariate techniques are really techniques when you have multiple outcomes. Multiple regression, you have multiple predictors. Those aren't outcomes. So, but at any rate, we learn the general linear model. Let's see if I can get the pen to work here. Again, bear with me, things slow down. It's just a kind of a pen doesn't want to go over there. Let me swap things around. I'm going to do a share on my other screen here. Give me just a second. I'm going to move you guys to the other side if I can. So let me stop the share real quick. And okay, so you guys see that? Okay. All right, so this is a bit of review, but building up to where we're at right now, right? So the general linear model, and there's a lot of terms in statistics. Statisticians apparently love the word general, so you see that a lot, general, generalized. So general linear model, we know basically the mean of that is equal to, for a general linear model, what is that? That's expected value of y, if you can't read it.
Our linear combination.
Yeah, so in terms of symbols, that's right. So in terms of symbols, what does that look like? Expected value y. In terms of matrices, like if you were to use matrix form here.
XB.
Yep. So that's x beta, right? Next step, we learned the linear mixed model. And we also have this for the marginal model, it's going to be the same, right? But we have in the linear mixed model, we have random effects. So the expected value of y given the random effects, what's this one? So it is true also for the linear mixed model, we have this as well for the marginal. But what is the mean given the random effects? Do you guys remember this one?
X beta plus ZB plus epsilon.
Exactly. Yes. So it's x beta plus ZB.
Mm-hmm.
Yep. Right. So we have the ability to add random effects in linear mixed models, and we also know that we can specify non-simple error covariance structures, right? Then we learned about generalized linear models, so GzLM. And for that, the link between the mean of the outcome and the linear predictor, we use G. So we have something like this. And in this case, we want to find a link between the mean of the outcome and the linear predictor that best suits the type of outcome that we have. So if we have a count outcome, we're going to use the log link. And that makes sense because it keeps everything positive. If we have a binary outcome, we use the logit link, and we get a very intuitive sort of S-shaped mean function that's bounded between 0 and 1 for the probabilities. So that's where we've built up to this point. And what we're going to talk about today are generalized linear mixed models, which essentially combine the principles of linear mixed models and generalized linear models together. So a GzLMM is going to look, on the left side, it's going to look like a generalized linear model. And on the right side, it's going to look like a linear mixed model. So we're sort of adding together these two principles to get to the generalized linear mixed model. Okay, so in terms of the broad overview, it should be a straightforward step when we think about generalized linear mixed models. Okay, now mu, that's just another way to say that's the same thing as expected value y, right? For a generalized linear mixed model, we're conditioning on the random effects, just like we would in a linear mixed model when we write it out this way, okay? And for all of these things, I'll add this. We condition on X. That's just a given. In regression, in frequentist regression, we condition on X. And you can add that in to all of these, but it's just so commonplace that we usually don't even write it. Okay, so we could have added X. We could have conditioned on B and X over there, but it's just a given, so to speak. All right, so we've learned general linear models, linear mixed models, generalized linear models, which you really need to distinguish the generalized linear model from the general linear model. The general linear model is just is for normal outcomes, non-correlated data, you know, what we learned in 66, 11, and 12. The generalized linear model, the ISD is the important part of that, is for other types of outcomes, you know, like the binary, binomial, Poisson, like different types of outcomes other than normal outcomes. So this is sort of a broad overview that I'm giving right now. And we're gonna kind of, through these next slides, kind of I'm just kind of rehashing some of these principles. So generalized linear mixed models, because of the fact that we're dealing with non-identity link between the mean and the linear predictor, there's greater complexities in actually fitting those models. And this, you know, I've made this comment before. Now that we have, you know, longitudinal data or possibly correlated data in some other fashion, the way that we write out the model, we need to identify the subject and the time as well. So we can do that with subscripts I and j. It's the same thing. Like this class really is a class in clustered data or correlated data. We call it longitudinal data because it's kind of a striking term that's catchy. And I'd like to keep it like that because most of the data that we look at are longitudinal. But to be honest, the methods that we learn are for correlated data in general, not necessarily just longitudinal data. So again, the generalized linear mixed model, on the left, it looks like a generalized linear model. On the right, it looks like a linear mixed model. And so all of these, one of the things that all of these models have in common is the word linear. So if we're dealing with a non-normal or non-linear link, then why do we call them generalized linear models and generalized linear mixed models? Why is the word linear still in there? What is the thing that's linear?
Is it because everything is like either additive or multiplied except for the link function, like the predictors and the random effects?
That's essentially it. When you focus on the right side, the function on the right side of the equation is linear. So the x beta, that's a linear combination of the parameters. And then you, like Matt said, you add that to the random effect. So everything on the right side, it's a linear function, right? And the link is really between the left and the right side. So when we say linear, we're talking about a linear function of the parameters on the right side of the equation. So for generalized linear mixed models, we still have the same distributions. Usually we assume that the random effects are normally distributed with mean 0 and some covariance structure, G. So the linear predictor, now for the generalized linear mixed model, instead of just x beta, we add the ZB to it. So the link is x beta plus ZB, or the linear predictor. Okay, the link is how you link that to the mean of the outcome. Just like we learned with linear mixed models, you can write a subject level form of it. You can write a complete data form. So if we have the complete data form, looks similar, but in this case, I don't have the subscripts I on it because we've combined everything together. Okay. Now, how do we actually fit that model? It's more complicated, a lot more complicated than the linear mixed model. Even the linear mixed model was complicated. So again, we're stepping up our levels of complexity when we go from the general linear model to the linear mixed model to the generalized linear mixed model. It's one added layer of complexity. And, you know, with the general linear model, things were really easy because you could actually write an algebraic form for your beta estimates and for your variance estimate. And then we go to linear mixed model, and we can write the likelihood in closed form, but we actually need a numerical technique in order to maximize the likelihood. There's not an algebraic form for the whole likelihood, even though we can get an algebraic form for the beta estimates. We need a numerical method in order to estimate the parameters in a linear mixed model. Now with the generalized linear mixed model, it's even more complicated because of the non-normal link and the model that we have in general is just more complicated. So we need to have more advanced approximation methods or some way in order to estimate the parameters that's more advanced than for the linear mixed model. So I'm not going to go through the methods too much here. I just want to give you the basic idea, you know, and kind of show you how complicated it is. And I'm not going to talk about the methods in great detail for it. But just to start off, the density for an outcome, this probably looks familiar to you if you're in theory, if you've had theory. Do you recall what this is? If you have a PDF, you know, for some outcome Y, we have the density for it, right? Density function, and we have we can write that equal to integrating over the random effects. We can write a conditional density times the density of the random effects and integrate over the random effects. Do you recall what that is? Does that look familiar to you? It might have different names.
Is that the denominator in Bayes' theorem also?
Looks like it, doesn't it?
Yeah.
Yeah, you're right. Mm-hmm. The name that I've theorem on total probabilities or something like that. Like if you can write this, like Matt said, you can write it in terms of a summation too. If you're adding over, if there's a variable, if B doesn't have a continuous but has a discrete distribution, then this changes to a summation, right? And that's probably the form you're used to seeing, like in the denominator of Bayes identity. I like to call it, because I like food, I call this the whole enchilada. That's my food association with it. This is how my wife remembers things as well, real easily, if she can relate it to food in some way. Okay, so if that's the type of person you are, then maybe that'll help you. So we're going to employ that, that identity or whatever you want to call it, in order to express the likelihood function for the generalized linear mixed model. So typically, like if we have independent subjects, we know that we can, in writing the likelihood, we can multiply the densities by each other. And if we log everything, then it's a matter of adding them up. Okay, so there's techniques that we've learned before that will also be useful in moving forward, in calculating or writing the likelihood and then then we have to figure out how to actually maximize it, which is the hard part. So, so we can write our likelihood this way. We're going to have to use a technique because we have distributions that, you know, we're not just dealing with normal distributions now, we're dealing with densities and functions that are more complicated in terms of how we integrate over them. And so typically what we do, if we're gonna need to approximate this likelihood function. And the way that we do that is to use what's called Gaussian quadrature. It's simply a method. If you have complex integrals, it's a way to change things over into a summation problem instead of an integration problem. So we express the likelihood. Here we have it in terms of there's an integral, you know, using the theorem on total probabilities, and then we change that into an approximate summation problem. Okay, so the Gaussian quadrature is a numerical technique to do that, and there's some detail at the end of these slides that go through it. I'm not going to spend that's the thing that I don't want to spend a lot of time on it, but if you're a numerical person, if you've had math and you're interested in those things, you can read through. And I've still sort of kind of given you the basics on it, but I think I just want you to know the basics, even more than that, just the principle of it. The fact that we have to find some kind of method in order to approximate the likelihood, that's the most important thing that we need to know as statisticians. These things are done, you know, when we call our procedures that will fit generalized linear mixed models. It will do all this stuff for us. Okay, so the software that we can use to fit generalized linear mixed models. I think you guys on your last homework, you probably got some experiments with NL mixed. Is that right? And in R, you can use the GlMER function. In the LME4 package. Did were some of you able to get that to work for this homework? So the LME4 package, we know that if you just use LMER, you can fit a random effects model, right? A linear mixed model. And so we can use GlMER to fit a generalized linear mixed model. And I feel like I feel pretty good about this package from my experience. There's certain packages in R that I'm less comfortable with. And one of those would be the NLME package. Sometimes I get it to work and other times it just doesn't look like it works too well. But the LME4 package, from my experience, it seems like I've gotten pretty decent results out of this. So I'm going to sidebar, actually. I'm going to ask Jonathan, did you get the linear mixed models to work using the Kronecker product?
No, I wasn't able to get the same result as SAS.
Okay. So you found a package that kind of came out fairly recently, right?
Mm-hmm.
And that's kind of what I was saying, is that things are developing, and I think it's a matter of time. I think things will be available in R to do those kind of things. And there's packages coming up all the time, but obviously, you know, I think they need to be tested to make sure that they can work. This one, again, I think seems to work pretty well. So so when we approximate that likelihood function, we're gonna basically, we're gonna be using Gaussian quadrature. Or you can say method equals Laplace, which is really equivalent to a special case of quadrature. We'll talk about briefly here in a second. So adaptive quadrature, you have to figure out the number of quadrature points to use in the approximation. So if I just go back to this slide here, when we change this integration problem to a summation problem, we're going to sum over k equals 1 to capital K, and that's the number of quadrature points that are used in the approximation. Okay, so adaptive quadrature, essentially the model or the method will pick for you the best number of quadrature points to use in the approximation. I think R, I think by default in R, it actually just uses 1 quadrature point, but you can specify the number. I'm not sure R has in this particular package if it has adaptive quadrature. I'm not sure if it does. Some details there on the quadrature that I'll let you guys read. So in terms of the code that we use, we can use NL mixed. NL mixed is good and hard, I guess. You can look at it one of two ways. NL mix is really nice because you can really specify the models that you want. You write the code yourself. It's less canned, which makes it harder, right? Like if you look at what I have to do in GzLMMI, this is the basic procedure that we have to fit a generalized linear mix model. Okay, so you can use proc GzLMMI. You can also use proc NL mix. And so NL mix is nice because you can specify things, but you have to use a little bit more code, obviously, in order to do that. So for the data that I have here, I'm just adding a random intercept. And we know that that's a pretty simplistic way to account for correlated data, but it's much better than doing nothing. Okay, so I would say, random intercept you've gone 80% of the way in handling correlated data. It's much better than not doing anything. But for longitudinal data, typically we're going to do better by, specifying something like a AR1, if we have repeated measures over time. But it's much, much better to do this than to do nothing if you have longitudinal data. For some types of correlated data, it may be the best way to go. Okay, so here we have eta. So this is our linear predictor that we've defined. Okay, so I have variables in the data. I have my pollution variable, day, weekend, an indicator whether it's a weekend or not, an indicator whether it's holiday, and then B, which is the random intercept. Okay, so it's kind of nice. You write your model. This is essentially the statistical model, at least the mean part of it, right? The linear predictor. And then we give it the link, and we're going to model exacerbations, which is our this is our binary. This is our binary outcome. So a kid will have a 0 or 1 on a given day, whether they had an exacerbation or not. So it's pretty rare. So it's going to be a 0 heavy variable, but it's binary. So it's either 0 or 1, and we're relating it to our predictors, and we tell it the appropriate link. We're using the logit link, okay? And we're saying that B, this is where we say that it's random. So this is how we define it as a random term here. Okay, so we've kind of laid everything out. So when you do the NL mix code, you have to understand what you're doing. You have to understand the model and all the specifications for it. With proc-glimix, it's more canned, and you can just say, it's sort of like GenMod, right? But it's just a step up, so we can add random terms to it. So with Glimix, we write the variables that we're going to use for the regular part of the linear predictor, and then we can add the random intercept in a separate line, just like we would with proc mixed. If we're going to use the GzLMM I function, it's even simpler than SAS in terms of, you know, a canned function. It's very, very short. We write the outcome as a function of our predictors, and then this is the random intercept here. And in both cases, we specify the type of distribution that we have, and that induces so the binary binomial induces logit link. Okay, so I think there's ways that you can say logit link, but by default, that's what we're going to get with these.
Hey, Matt,
Yeah.
can you go over the parameters that you're picking in the first line of that NL mixed code?
Oh, yeah. So that's a good question. This line here, these are starting values. So in the numerical method that we're employing in order to fit the model and actually get estimates, if we don't say anything, it will probably work. But what we're doing is we're giving it starting values for parameters in the numerical algorithms. So it's quite like, sorry, somebody was,
Is it just like the means of the variables, or how do you?
yeah, so how do I pick them? So there's different things you can do. One basic thing would be to just take a GenMod, which ignores the correlation, and get your estimates. So yeah, obviously I have to have some idea, you know, what they are, and so from experience, I know that they're roughly around these values. And so one way you can do it is, you know, for example, just do GenMod or something, ignore the correlation and get estimates. Just so I'm doing this, so I'm kind of giving that numerical method a little advantage. So it doesn't have to start from you know, some crazy values. Now, the thing is, some of these numerical techniques will start from like a generalized linear model, naive approach. You know, it will use those as starting values. So I'm trying to remember if I tweak them away from even further away from that, just based on initial runs of the model, you know, some trial and error possibly that I did, but my general statement would be, you know, that's probably the most straightforward way to do it. Just ignore the correlation. If you use GenMod, you can get estimates, and so you're starting it from, you're giving it a little bit of an advantage. The one thing that we wouldn't have there, there's one term in there that we wouldn't have by using GenMod, right? And that's the variance of the random intercept. So we have to have some way of looking at the data to get an idea of approximately what the variance is going to be, you know, the subject heterogeneity would be, in order to get this one right here. So these are all related to that. So again, it's possible we get the same answer even if we took this line out, but maybe not. Maybe it would just have problems finding the maximal point. So we're just giving it a little of an advantage by using starting values that we know are approximately right.
The S2U value that you set, I'm wondering, I see that it then goes to STB or S2B rather.
Yeah, I don't know. I think it should be the same. That's
Okay.
a good catch. I think I was changing what I did was I used to call random terms U, and then I transitioned everything over to B. And I think in this case, I just forgot to change that letter. That's a good catch, but I think that should be.
I think you're right. It's okay, Matt, because the S2 above there is for the model, but this one here, the S2 above there is not going to estimate the variance, but the parameter estimate of that random term. While this one here in the normal is the variance of B. So I think it can take any name.
Huh.
Yeah.
It can take any name, but it won't use what we said in this statement though, right?
Yeah, so what we said up there is actually the parameter estimate, but not the variance, because it is a term. So it is like a beta. It's like a beta, but not necessarily the variance.
Yeah, let me double check that could be true. That you're saying this is only for fixed effects. Is that what you're saying?
Yeah.
Let me double check on that. It's possible you're right, but let me double check on that one. You sound like you know what you're talking about. So, any other questions on the code?
Yes. Can you hear me?
Yeah.
I have a question about the Poisson and the binomial, because in those two models, we don't have error term, right? That means we don't have the variance structure of R, right? And then in the random statement, in fact, what we introduce is put all the variance into the G matrix where.
Yeah. So Randy, that's a great thing that you're getting on here. We don't have an error term in these models, and that's true of generalized linear models and generalized linear mixed models in general. Sorry, I use the word general again. So when we, again, for a generalized linear model, we have this, right? And for a generalized linear mixed model, we have this, and that's how we write it. And you notice that there's no error term there. And so that's one of the things about generalized linear mixed models. Usually we don't even have an error term. So we don't specify like an R matrix or anything like that. And so that, because we've eliminated that issue because we're considering the mean, we're linking the mean to the linear predictor directly. There's no error term there. So in our models, we don't, any of this code here as well, we don't see any error term. We're just specifying random effects. So we're specifying B here through this last statement. Now I'm actually going to talk about one method on Wednesday that we will actually have an error term. But really for the generalized linear mixed model, this is the model, right? So we still don't really have an error term in there. And that's good. I was going to actually, I had that written down to say that, but thanks for bringing that up again to emphasize that. Anything else?
Is there a reason why you selected 7 for your G point?
I believe I did that because in GzLMMX, when you say method equals quad, it's going to use adaptive quadrature. So this is going to be adaptive quadrature. And I believe that it uses 7. It figures out that 7 is the right number to use.
Is it
The
because
number
you
of
have 7
quadrature points.
betas?
It's dealing with, it's not the betas, it's dealing with how many, where was that? Here it is. It's when you do this approximation with Gaussian quadrature, if you use more quadrature points, you're going to get a better approximation. Okay, so it's basically just a number that expresses how much you're using in order to get a better approximation.
So does increasing your G points increase the computation time?
Yes, and that's the trade-off. That's why, like you may have been getting at this, is like, why not just pick a big number, you know, to make sure it's more accurate. Well, it's computationally, it just becomes a burden if you pick too many points. And so you have to figure out the number that's enough so that you get a decent approximation, but not too much so that it really slows things down. That's the goal. And the reason why I had to write 7 for the R approach is because it doesn't do, to my knowledge, it doesn't do adaptive quadrature, so we have to tell it. And I wanted to compare SAS to R, and that's why I did that. So using the data that I have, this is exacerbation data from National Jewish. And so we look at kids over time. Did they have an exacerbation on a given day? And how does that relate to those variables that I have in the model, the fixed effects? And I'm allowing for correlation within a kid by adding the random intercept. Okay. Now, if I have data collected over time, how good is that? Well, we might get an improvement if we use the AR1. But again, the issue here is we can't specify the error covariance matrix, right? So the way that we're doing it now is by saying, let's add a random intercept. And so we're at least identifying that we have kids, and we're distinguishing, two measures within a kid versus measures that are between two different kids. There's just a few more technical points here on slides 10 and 11. I'm going to jump to the analysis here of the data. So this is the exacerbation data. Getting a little too high there. So I think there are about 45 kids, and we're looking over several months, and we're trying to figure out what's the association between exacerbations and air pollution, a linear time trend, whether or not it was a weekend, whether or not it was a holiday, and then we have the estimate of the variance for the intercepts for subjects there. And right now, I'm just more focused on how do using these different approaches compare to each other. So use NL-mixed, use GzLMMX, which is more canned, and then I use GzLMMI in R. And I would say these are pretty close to each other using these different methods. And this is using 7 quadrature points. Okay, so next we can look at the estimates themselves to try to get a sense of how do these predictors relate to exacerbations. So what would you say when you look at these parameter estimates? Anything striking here? And this is actually a good exercise because we don't see the p-value. So you're going to have to look at the estimates and you're going to have to look at the standard errors. You know, what do you typically do first? The first thing I would do is look at the direction of the estimates to try to understand if the direction makes sense. Look at the estimate relative to the standard error to get a sense of how significant it is. What would you use as a guideline to decide how significant something is? Go ahead, Benjamin. Sorry, go ahead.
Find the confidence limits and check if, depending on the ratio, if it crosses 1 or if it includes 1, that would be like a significant value.
Okay.
Not non-significant, but if it doesn't include, that would be significant.
Yeah, that's one thing you could do. Can you do that roughly by looking at the estimate and the standard error? This is for anybody. About how many times bigger should the estimate be than the standard error for you to start thinking, oh, there's something there?
Well, if you just multiply the standard error by 2 and then like subtract it or add it, if zero's in there, then you know.
Yeah, I think that's pretty good. Like if you can look at it and it's at least 2 times bigger than the standard error, then that's going to give some indication, right? Because we know that 95%, like plus or minus 2 standard errors, that gives you 95%, right? And plus or minus 3 gives you, pretty close to 1. So, if the standard error is not 2 times bigger, then it's not going to be significant, right? Now the level of the p-value I think is important, but that gives us a frame of reference, right? So what are the effects here that look like they're going to be, significant?
Can you talk about why you can use your confidence intervals that are based on normal distribution for these non-normal outcome?
Well, so we have non-normal outcomes, but in terms of like the estimates of the parameters and tests for them, think of the Z. I think we're probably gonna use, in most cases, we're gonna use T or Z methodology to do inference on the specific
and some survival
parameters.
Like Cox proportional hazards, you don't typically use the normal for your standard errors.
For what? Say again. I'm sorry, my furnace is running back here.
For some survival analysis methods like Cox proportional hazards, you don't really use the normal.
Yeah, but for generalized linear mixed models, and that's something I haven't talked about here yet, but we're gonna typically use T or Z methodology in these models. So you can think of if we think of Z, Okay, if we could use a Z approximation. So the estimate over the standard error, I'll just say that. Okay. Now it's possible that we can refine that using a T, you know, if we can incorporate variability in our standard error estimate due to unknown covariance parameters. You know, we might be able to use T, but as the sample size gets large enough, it's going to be approximately standard normal. So let's take one in particular, right? So let's look at weekend. So we have so for weekend we have negative 0.2338 over 0.1392, and that's going to be equal to, what is that? Somebody have a quick calculation. It's less than 2, greater than 1.
$1.68.
Thanks. So 1.68, right? So,
and it's negative.
yeah. So the p-value, like for a z-statistics, that's that has that two-sided p. Guessing around 0.1 or something, you know, because for a standard normal, if we had a value of, so if we have 0, we have 2, negative 2. If we had a value of 2 for a two-sided p-value, we'd be doing both sides, right? And that would be 0.05 roughly. So a little bit less than 2. I'm saying the p-value is about 0.1. I could be off a little bit, but maybe somebody can check on that. So we're using the basic Z, you know, a large sample Z ideas here. Are there any parameters, estimates that look like they'll be very significant?
Beta 0, the intercept.
The intercept, yes, definitely. And that's usually the case. Usually our intercept's going to be significant, but that definitely is. Anything else that you see there? What about day? You look at that, it's like 8 or 9 times. The estimate's 8 or 9 times the standard error. So again, don't get tricked into looking at the estimate itself and saying, oh, that's really small, because that's unit dependent. And so day, we know just by looking at the estimate and the standard error that we're going to have P is less than 0.05 for sure, much less than 0.05 by looking at it. So what's that saying? It's saying that, you tell me, what is that? What is day saying there? It's a continuous variable in the model. And we have a logit link with the outcome, and that's related, so that we're looking at probability of exacerbation. So how would you generally interpret that estimate there?
Is it that the odds of exacerbation increase over time? Like
Yes.
this, the day is
Yeah.
your time variable, right?
Yes, that's right. So odds of exacerbation are increasing because it's positive, right? And so why is that you know, there may be something that's happening. For example, if we go from a period where there's more allergens or something in the spring, possibly later in the study, that's increasing their chances of having exacerbation. Or maybe the weather's getting better, they're going outside, exercising more, and there's probably another variable in there that's explaining why they're getting more exacerbations over time. And that's something we could look into, but that's the most significant predictor in there. What's interesting is that pollution, there's actually negative relationship for the data that we have here. So this is saying that when you increase air pollution, you're actually decreasing your odds of an exacerbation. Now, I wouldn't get too concerned either way about that, because look at the standard error in relation to the estimate. It's not going to be significant. But again, there could be confounders that might explain it if in fact that negative estimate has any meaning to it.
So, Matt,
Yes.
do we typically use the term average increase in odds, or the average term doesn't matter?
Average matters. Yeah, you're right. And I've like, when you write a statement, it's very important to include that, because that's really what we're making inference for, is for an average. You're absolutely right about that.
Okay.
So the point of all this is, we're able to, we have binary data, and now we have a way of dealing with correlation in the data. Now, some of you, I think Carrie, you had a binary for your project? Are you considering a binary outcome?
I was, but I don't know if I'm gonna do it.
You're not anymore?
No, we didn't end up getting the variable that links all the people. So
Okay.
for the data set I wanted to use.
Okay. Does anybody else have data for your project where the outcome is binary?
I do.
Laurel, can
That's what I'm
you
looking for.
mention what that is real quick?
Yeah, so I'm thinking about looking at hate crimes in Denver. So the outcome is if action was taken, so like an arrest was made or a citation was given, versus action was not taken in response to the hate crime.
Interesting. Is that like recent data, like from 2020?
Yeah, so it's 2010 till let's see, January 4th of this year. But I'm reaching out to the people that are doing it and asking if they have more data from this year.
Okay.
But fully up through 2019.
Okay. So so the methods we learned today and Wednesday will be, useful for those of you that have binary outcomes. And it's good that Laurel has one. I'm hoping that at least a few will have binary outcomes, so that we can see, these methods applied to different data. Now, this is one real basic way to do it. We've just added a random intercept in the model. What I'm going through towards the end of these slides is just comparing so I'm comparing the different approaches. This, I'm actually using just one quadrature point, and I'm showing how to do that in Proclimix and then GzLMM again. So I'm just showing you variations of fitting the model using, more or less quadrature points, comparing SAS to R and things like that. And then what I do after that in these slides is I show why this likelihood function is so complex. You might be wondering why is it different than the normal likelihood that we have in linear mixed models. And so I just give an example. Again, we can write the likelihood using the whole enchilada thing. And then we can, if I'm using a specific example where we have a binary outcome, where we have the logit link, and we have normally distributed random effects. So that's summarized here. And just reworking it, you can express the probability that you have an event, or probability y is equal to 1 is equal to that. This is the S function that you get when you have the logit link. And so I'm not going to, I did this before. I actually gave a homework, you know, kind of related to this, you know, derive the likelihood, express it, and stuff like that. This year I'm not going to do it. But if you're curious, you know, this just shows you it in steps what the likelihood looks like in this situation. And integration is very difficult when you have e to the negative b squared. Something like that is very complex. And when you actually have, like, when you actually maximize the likelihood, you're going to put values for x and y in there. And you, for this binomial outcome or binary outcome case, you know, I'm just showing that one piece of it for one subject. You're going to get an expression that I have here, you know, for this particular data, even just pretty simple values of x and y. This function that we have, when we integrate over the random effects, that's complicated, and we need that Gaussian quadrature in order to approximate it. So I'm not going to test you over this, but you know, just the basic idea is that we need to use a numerical technique to approximate the likelihood, and then we can use you know, the GzLMMX or the GzLMMR function to actually carry out the estimation. So far, you know, we just talked about, you know, adding a random intercept. That's a real basic way to handle correlated data. If we can't specify the R matrix, can you think of what else? What would be a next step that we could do if you can't specify R? What's the next thing that you might try if you want to be a little more sensitive to repeated measures over time? That's my last question. These slides, I'm just going to allow you guys to browse through those. But I do want to get your thoughts on what you would do if you can add random effects, but you don't have like a repeated statement that you can add up to this point that we've learned so far. What do you have any thoughts on what you do in getting a more time-sensitive model?
Can you do like a random slope maybe?
Yeah, that's what I would do. That's exactly what I would do. I would add a random slope for time. So you have a random intercept, random slope for time. And that's going to be a little more time sensitive, right? And we actually learned that in the last homework, that when you add random terms for time, and then you have, especially if you have an unstructured for G, that you actually are inducing a correlation structure that is a little more time sensitive, right? That was one of the homework questions that we had. So, and another benefit of that is that you can look at subject specific trends. So you can see if one particular subject tended to be going up or tended to be going down. So there's a couple benefits by adding a random slope for time. Now, once you make a generalized linear mixed model more complicated, there's always a question about, is it going to fit? You know, it's a much bigger issue for these types of models. Is the model actually going to fit? So that If it does, and if, you know, and if it looks like you improve the fit, we know that we have something that's a little more time sensitive in terms of modeling correlation. So that's what I would do. You could even try quadratic possibly, and see if, because you get even more time sensitive benefit by doing that. You know, but you know, you'll have to figure out if it's worth it or not when you do that. So today we learned about, you know, how you approximate the likelihood in a generalized linear mixed model. On Wednesday, we're going to talk about a totally different approach to fitting a generalized linear mixed model. And it's actually my favorite way to do it. Not necessarily saying it's the best, but it's the way I like personally. It's my favorite. So we'll learn about that on Wednesday. Real quickly though, I wanted to look at the homework 4. Where'd you go? Okay. So so homework 4. This is a good homework because you learn about how to take a combination of random effects and non-simple R in order to obtain a variance or covariance matrix for the outcome, right? And so we do that in number 1. You can see how you're not restricted by just adding random effects or just adding a non-simple error covariance structure. You can do both. And you know, somebody asked a question before, you know, like really, or you learned how somebody told you really should only do one or the other unless you have a good reason. Well, I feel like for me, my goal is to find the best covariance matrix for Y. There's something that makes the most sense. You want to be parsimonious. In other words, you want to be frugal. You don't want to spend a lot of parameters. You don't want to just make the error covariance matrix as complex as possible and add in a bunch of random effects, because you could be over specifying the model, overfitting it. So you do want to be parsimonious, but I don't think there's any problem with adding random effects and a non-simple R structure in your model. And I do that quite often. So one of the questions is, do you have the software that will allow you to do that appropriately? So one of the things I want to mention though, like in number 3, you know, we fit the Kronecker product structure. And this is one of the things that happens sometimes, is the one that makes the most sense may not fit. And that's what happened with this data. We use to me, it seems like the AR1 structure for time and the unstructured for group makes a lot of good sense. And it doesn't introduce that many parameters because we only have, you know, for group, we have 3 groups. So I think there's 6 there. And then we have 2, but one of them is going to fall out. So there's actually 7. There's 7 parameters with this first one. That seems like it should work well. For some reason, it didn't fit. There's times when I've played around with the settings on the numerical technique and actually got it to work, but you got to be careful with that and not get too lenient of a convergence criteria, because it may not actually converge to the right place. So you do have to be careful. But if you use the un by un, you get a 324 value for the AIC. You actually do get a slightly better value for the un for time and CS for group. 317. So in part C, you were asked about using a different approach. And if you use the random intercept, that's one possibility, and you should get full credit for that. So we're going to go back and make sure you got full credit for that. It's not very good in terms of the value that you get. compared to the Kronecker product. I actually found one though that was pretty close just by playing around. So I got pretty close, 321. And the way I did that was I added a repeated statement for time. So we have, if we think about this, we have CH, CL, CO groups. And then we have time, something like this, 30, 0, 30, 60, 90, 120. And so we have to account for repeated measures in 2 dimensions. And my thought was, okay, let's try to get an AR1 structure. And it doesn't seem to work if we, by doing the regular Kronecker product, but if I specify ID within group, I'm accounting for these correlations here, going this way. So that's what I'm doing by using that. But I know that we should account for correlation between groups as well, because dogs, we repeated the measure, we took measurements over the treatments on the same dog, right? So we should account for correlation that way as well. And so that's the way I did that, was by adding a random intercept for the dogs. And so that's going to account for, helps account for between treatment correlation. So this took a little playing around with, but again, I'm doing a combination of the repeated and random statements, or specifying the covariance structure for the random effects and the covariance structure for the error. And my goal is to have a combination that's going to give me a decent V, or variance of Y. Okay, that's possible you could find something else. I didn't spend too long on this, so there could be something else that's even better. But I think this is a good way to kind of really understand how we take a combination of the random effects and the error covariance structure in order to get the variance for Y, which is the main thing that we're interested in.
I have a quick question, Matt.
Yeah.
When you start looking for these variances in this type of manner, for example, the Kronecker product with the UN and the compound symmetry, so that was a pretty good fit. But what's the likelihood of so now you have a good fit using a variance covariance structure that doesn't make sense. What happens when you have more data? Is it possible that now your AIC will be lower than a different variance covariance structure that does make sense?
Yeah, I would say if I get more data for this, I would go back and I would try the AR1 by unstructure, the one that conceptually makes the most sense. That's the one I really want to try. And so I would certainly go back. If I had more data, I would try that again.
Okay.
Again, you know, and the thing I'll leave on today is why are we concerned about correlation? Why is, you know, when we report our results, what we're typically doing is reporting the beta estimates and their standard errors. We might report the covariances, but typically that's a secondary thing, right? So why do we worry about all this stuff? Why do we worry about all these different structures?
Because it affects your type 1 error.
Yeah, so it affects your type 1 error, and more generally, it affects the standard errors of the estimates. It can affect them a lot. It's probably not going to affect your estimates, your beta estimates themselves. It might actually a little bit, but more often it affects the standard errors of your beta estimates, you know, the structure that you choose. So you want to get the structure that's the best, right? The best possible one. Now, there may not be huge differences if you, let's say, like in this case, between the un by un or the un by CS, that may not end up mattering that much in terms of inference for your fixed effects. But still, you know, it's best that we pick the one that seems most appropriate based on both on conceptually what makes sense, but then also what actually works, right? We have to go with the best one that works. And so for the data that we have in this case, it looks like the un by the CS. If you use un by un, I think that's probably okay too in this case. Any other questions? Well, it looks like I'm in my basement, but it looks like the sun's actually out, so that's a good sign, right? And I think it's actually going to warm up this week. So get out, enjoy a little sun, and we'll talk again on Wednesday. So good to see you.